So we're talking about how do we find solutions to non-homogeneous differential equations. And so there's two methods. So again, just to emphasize, here we're trying to do the find our y sub p for our non-homogeneous differential equations. And the method for today is called the method of undetermined coefficients. In some sense, you might say it's a method of really informed guess. And then we say, we know roughly what the solution should be for f of x. We just have to nail it down. It has a very particular limitation. In particular, we have the two sides. So over here on the left-hand side, we say, well, the kind of differential equation we have over on the left-hand side, this is our favorite kind. So we need to have constant coefficient, and then of course we throw in the usual suspects and, well, linear. It's not homogeneous because there's f of x, but we need something that's our constant coefficient. Otherwise we can't use this technique. It won't work. But there's also this side, the right-hand side, the non-homogeneous part, that f of x. That also has to have a limitation. And namely, it can't just be any arbitrary function. So what can it be? Well, it has to be a solution, and I'll put that in quotes, to some homogeneous, and of course this is the point where we're like, why do we use such long words? Constant coefficient, linear differential equation. So in other words, it has to be nice. If it's not nice, it's not going to work. And so what do nice things look like? Look like x to a whole number, maybe an exponential part, maybe a sine or a cosine part. But that's it. Those are the only things that come out of our homogeneous constant coefficient linear differential equations. So in that narrow setting, if we're there, then we have a way to solve. So how does it work? Well, what we do is we start by saying, all right, find the homogeneous solution. So in other words, you set f of x to 0. What's that complementary solution, y sub c? And you say, all right, now after you've done that, the next thing we're going to do is we're going to find the pieces that make it up to some constant. Another way you can think about this is really we're going to say we're going to make a mold, or we're going to find the form. We're going to say, look, we know our solution looks like something a times this function plus b times that function plus c times that function, so forth and so on. And we're going to do lots of examples. But here's the process. You take each piece of f of x. So when we talk about a piece, things separated by plus or minus signs. And say, all right, each piece of f of x should contribute a term. And then if there's a power of x, make sure you have all the lower powers of x as well. Next, make sure you add sine and cosine so that sine and cosine pieces come in pairs. So if you just see a cosine for f of x, you also have to throw in the sine. And then the last thing. You want to make sure there's no overlap with what you found in the first step. So that's why we bothered to find the complementary solution. We have to say, hey, if there's overlap, we need to do a bit of a bump. Bump up so that there is no overlap. So you found the form, your mold. And the last thing is say, look, your particular solution has to take the form that you find in step 2. So we say, great, feed it into the differential equation and set your coefficients equal, figure out what they need to be. All right, maybe we should do an example of what we mean here. Okay, so let's just make up a differential equation really quick. Say y double prime plus Well, let's do minus. Y double prime minus y equals x e to the x plus 3 cosine x plus 7. Why not? Something simple. Right? Okay. So some of these things we can hopefully do almost in our head. Y double prime minus y. What does that look like in terms of the solutions? Think of the algebra problem. What's the algebra problem? R squared minus 1. What are the roots? Plus or minus 1. So we say, hey, our particular solution, our complementary solution, which is just for this part, well, looks like something e to the x plus something e to the minus x. All right, so that would be step 1. So what would step 2 look like? We're not going to do step 3 because that might take a while and also take space, which we don't have. But our particular solution. All right, so what you do, how many pieces do you have? You have 3 pieces. You go to your first piece, you write it down. That's what we mean when we say take each piece. Just write it down. Is there a power of x here? Yes. So what do we need to do? Well, according to this, add anything with a lower power. So what's a lower power of x to the 1? X to the 0. So you'd also have another piece will look like e to the x. So that's what we mean here by adding pieces for anything with a lower power. Here was x to 1, so we have x to 0, e to the x. The other parts stay the same. Okay, are we done with that piece? Yeah? Okay, so come to cosine. All right, that's going to be a piece. Any lower powers of x we need to worry about? No. Do we need to worry about the 3? There's a 50-50 chance, yes or no?
Yes. No.
Okay, there was one yes, some no's. The answer is no, not here. Because we're going to take linear combinations. See, we're going to throw in these arbitrary constants. We don't know what the coefficients are. We're finding this, see how it says up to ci? The ci are our coefficients. Okay, how about for the 7, what do we put down? That's a piece. What goes there? It's a function. It has to be accounted for. So we can think of it as 1 if you like. All right. So that was the first bullet point. Second bullet point. Do we need to add any sine or cosine terms? Which one? Yeah, see, because of the cosine, we'd have to add the sine. All right, anything else that needs to be done for the second bullet point? No, we're good. All right, now the last bullet point. We say, look, you have to bump up any pieces so that there's no overlap with YC. Now, when we talk about bump up means multiply by a power of x. So that's, whenever I say the phrase bump up, in case you're wondering, what does Steve mean when he says bump up? You have to multiply by a sufficiently large power. So, our pieces for our complementary solution are e to the x and e to the minus x. Is that showing up anywhere in our list? The e to the x. Okay, so that means we have to bump that up. So, how do you bump? Well, we multiply by x. What power of x do we need to multiply by? Well, in this one, I just multiply by a single x, but here what would I do? Multiply by x squared. So I have to bump up the pieces so there's no more overlap. But whatever, of course, the e to the x is, that whole family is being bumped up. All right. So the punchline is, our particular solution is some combination of these functions. And what we mean by that is that there's a series of unknown coefficients. So some constant C1, some constant C2, and so forth, and so forth. So in particular, there's 5 unknowns. So when we talk about undetermined coefficients, these are the undetermined coefficients, the C1, C2, C3, C4, C5. And the last thing for us to do is to determine them. So how would you do that? Well, you plug it back into the equation y double prime minus y, and you get out what happens. Then you compare it to the right-hand side, and you say, all right, how do you pick your C's? And we'll do an example in a few minutes. So that's the idea. I want to try to give a little bit of motivation without getting into too much technical detail. So let me see if I can do this. All right. Imagine we have a differential equation. So the left-hand side, that's our differential equation, equals f of x. And we look at this differential equation, we're like, what can we do? And a thought occurs to us. It says, hey, you know, f of x is nice. In fact, f of x is so nice, there's a nice differential equation for f of x that we can throw it in, and out comes 0. And so we're like, well, that's great news for us. So what we do is we do that to both sides. So we throw the left-hand side into this differential equation and the right-hand side into that differential equation. Now the right-hand side is going to do what? Become 0, because that's how it's set up. The left-hand side, well, it gets bigger. It blows up a little bit. So it's sort of a bigger differential equation. But it's still constant coefficient. It's still linear. So now you're like, wow, constant coefficient, linear, homogeneous differential equation. Homogeneous because this is 0. Our favorite kind. And we actually turned out, we can say a bit more. Say, look, it has on this side the same roots as we started with, plus a few more roots. And where did those plus roots come from? Well, they came from what you used to cancel out the f of x. And so we're like, so that means that our original solution to this differential equation is also a solution to this differential equation, and therefore our solution has the following. It comes with your old roots, so that's the original left-hand side, plus some new roots that you acquired from this differential equation. And so the new roots, that corresponds with the pieces that make up that new particular solution. That's what we're really forming here when we talked about the process. We were saying, hey, when we have this, we have our new roots. And the reason we had to do our bumping is we had repeated roots. And like, oh, e to the x was already inside our old root, so we needed to bump things up when we had them as new roots as well. Okay, so that's sort of the philosophy. The details are essentially all there, but we won't go into the details because practice is good. All right, any questions?
Could you go over the first bullet point for step 2 again?
The first bullet point. Well, it says we're trying to make up our particular solution up to, we don't know the coefficients, but we say, okay, we have to say, how do we find the parts? Well, we say, we have parts here, so we grab the function. So that's how we grab the function. Doom, doom, doom. So the x, e to the x, the cosine x, and the constant. Those were parts. But we have to say, hey, if you have a power of x, like x squared times something, or x cubed times something, you have to make sure you have all the lower powers of x as well. Because the rule is, you know, the powers of x build up. So if you have a high power of x, that means something had to build up to it. So that's why we have to include lower powers of x. So basically what you should think of is your solution are the pieces of your right-hand side with unknown coefficients plus enough extra to account for things like lower powers of x, sine and cosine come in pair, and just any overlap. So that's what we're doing, is we're just sort of saying, take the right-hand side, that's essentially it, just fix it a little bit, patch it up. Most of this is just saying, how do you patch? All right. And as we do examples, things will become a little more clear. So, example. Find the form. So here we don't actually have to solve for our coefficients. We have to find the form. It looks like there might be another question.
Sorry, real quick. When you do
No.
the lower powers, do you
Yes.
just go one power lower, or which?
All the way down. As we'll see. You got to go all the way down. Yeah. So you'll notice it doesn't say here just one lower power, but anything with a lower power. So if you have x cubed, you'll have x squared, x1. So you should cross your fingers and say, please don't give us x to the 17. Please don't give us x to the 17. Because if you do, the 17 pieces right there. That's when you say, computers are nice. We like computers. All right. So find the form, y sub p, for the following ODE problems. You do not have to explicitly find the coefficients. So we're just trying to say, hey, what does our solution need to look like? All right. So you might notice something. They share a lot of things in common. They all have the exact same right-hand side. Does that mean that our y sub p is going to be the exact same for all of these? Yeah, not necessarily. So this is just, as we'll see in a few minutes, going through here. All right. So they won't all be the same, but we always have the same initial guess. So our initial guess for y sub p, well, we grab our function. What's our function? If it helps, I'm pointing at it. Yeah, you don't need the 5 because constants are going to be, or we have undetermined coefficients, and so that's constants. So we don't need to worry about the constants, but we have that x squared e to the 2x. Do I need to have any other pieces? What else? Yeah, the x powers has to go down. X e to the 2x, then it would be e to the 2x, x to the 0. So our initial guess would say, hey, our unknown, well, our form, I should say, for y sub p would look like this. We don't need to worry about sines and cosines because there are no sines and cosines, which is good. What do we have to worry about? Yeah, we have to ask the question, is there overlap with the homogeneous part? So the answer will be this after we correct for overlap. So that's what we need to think about. So that's why we might have different answers for these 3 different questions. All right, well, so we begin. All right, so for part A, we have our differential equation, y double prime minus 4y prime plus 3y. And right now, we're looking for the overlap, so we're solving the homogeneous part. What's our algebra problem? R squared minus 4r plus 3 equals 0. Does this factor? Yes. What are the factors? Yeah, r minus 3, r minus 1. So what are the roots? 3 and 1. Okay, so that says here our yc, well, e to the 3x, I should throw in I hate that I'm using a there. Okay, all right. Keep working my way through the alphabet. d e to the 3x plus e to the x. Is there any overlap? So in other words, look at this. Does e to the x, is that any of the pieces? Answer's no. So since there's no overlap, then there's no correction, and therefore it's just what we thought it was. Say, great. Life is good. All right. So for part B, run out of space here at this rate, but, well, we'll make it work. Y double prime minus 3y prime plus 2y equals 0. What's the algebra problem? R squared minus 3r plus 2. How does it factor? He says as he writes it down like it'll factor. R minus 2 times R minus 1. So the roots are 2 and 1. So our complementary solution looks like something e to the 2x, something e to the x. Is there overlap? Yes. By how much? Yeah, there's just one piece of overlap here. So what do we need to do to fix our initial guess? Bump it up. So we're going to be bumping up everything. All right, we don't just bump up this piece, because if we bump up this piece, then that matches. We're like, got to bump that one up. So you have to bump up the whole chain. Everything moves one step up the ladder. So we say, great. So our answer, just multiply by x. Ax cubed e to the 2x, bx squared e to the 2x, and cx e to the 2x. All right, one more to go. Part C. Y double prime minus 4y prime plus 4y equals 0. Well, okay, you probably can guess where this is going. Does it factor? R squared minus 4r plus 4. Yeah, r minus 2 times r minus 2. So that says our roots are 2 and 2. So our complementary solution is something e to the 2x, and because it's a repeated root, have to add an x. Okay, so do we overlap? Yes, I should point to this one. Yeah. And not just by one, notice we overlap by 2. So what do we have to do here to fix? Got to bump twice. Got to keep bumping until there's no more overlap. So our particular solution would be the same function, but now multiplying through by x squared. So ax to the 4th e to the 2x, bx cubed e to the 2x, cx squared e to the 2x. So that's sort of, this is just a reminder, you have your initial guess, but be careful, it depends. It depends on what's happening with your original differential equation. All right. Well, good. Let's, Okay. Are you ready to try a problem, or should we do one together first? All right. Hopefully you were taking notes. Determine the appropriate form for a particular solution of the differential equation y double prime plus 4y equals 17x cubed sine of 2x minus 7 cosine of 4x plus 5x e to the 2x plus x cubed. You do not need to solve for the value of the coefficients. All right, so first off, we just do a quick check. Y double prime plus 4y r squared plus 4, well, equals 0. R squared plus 4 equals 0. So the roots are plus minus 2i. So our complementary solution, which we have to worry about, I'll use C1. Okay, so it would be, what are the functions? Cosine 2x and C2 sine 2x. Okay, good. For reference. All right, so we begin. We start with the first piece. X cubed sine 2x. So we'll just write it down. We have an x cubed. So what do we need to do? All the power is going down. X squared sine of 2x. X sine of 2x. And sine of 2x. Okay, so then we'll have those pieces. What else can we do while we're here?
I remember earlier in your class you said whenever you had sine of 2x, you had sine involved with differential equations. You had to have a corresponding cosine as well. Is that not true here?
It is true, yeah. So people said, hey, remember sine cosines have to come in pairs. So we'll write the matching set. X cubed cosine 2x. X squared cosine 2x. X cosine 2x. And cosine 2x. Now that's just that one part. And we're not done with it. We'll come back to it. Okay, cosine 4x. What's that going to do? Cosine 4x. Life is good. But what should we go along with that? Sine 4x. All right, then we go to our next piece. X e to the 2x. Well, what's that going to do? X e to the 2x and e to the 2x. Got to work your way down. And then we get to another piece. X cubed. All right, what else do you need? X squared. What else? What else? All right, now that's almost it. But what's our problem? We have to check for overlapping. Do we have overlaps? Yes. So that says all of these have to go up by power of x. So this will be x, x squared, x cubed, x to the 4. Now those are all our pieces. And the last thing is throw in your coefficients. So our particular solution looks like A plus B plus C plus D plus E, F. I feel like today's class is brought to you by the letter, well, let's find out. J, K, L, M, N, fancy O, so it's not 0, the letter P. So I think that's what, 16 different?
Do we not have 2 overlaps in this case, and we don't have to bump up by 2?
Well, but we're only overlapping sine of 2x just the one time. So it's the sine 2x ladder that gets bumped up once, and the cosine 2x ladder that gets bumped up once. So we don't need to say x squared sine 2x, because x sine 2x is not part of our complementary solution.
But we don't need to bump up any of those terms.
None of the other terms need to get bumped up because none of the other terms are part of their complementary solution.
How come the negative in the cosine 4x doesn't translate to our solution?
So any coefficient, so the question is, what about this negative? Any coefficients don't matter because they're all going to have these unknown coefficients. So they just get absorbed into those unknown constants. So they don't make a difference. So this shows you how to set it up. But of course, we'd never ask you to solve a problem like this. Instead, we'd ask you to solve a problem like this. So we're actually going to carry through with our third step. So far, we've talked about setting things up. Okay, so find a particular solution for y double prime plus 4y prime plus 4y equals 18e to the x plus 8x squared. All right, let's start with our homogeneous function. Y double prime plus 4y prime plus 4y equals 0. What's the algebra problem? R squared 4r plus 4 equals 0. Does it factor? He says, as he writes it down, as if it's factoring. And r plus 2, r plus 2. So our roots are repeated, negative 2. So we look like e to the negative 2x times some number e to the x e to the negative 2x times some number. Looking ahead, are we going to have to worry about overlap? You can oftentimes look at this and say, aha, I have to worry about overlap, or aha, I don't have to worry about overlap. In this case, no overlap, because there's no e to the negative 2x terms. So life is good, no bumping involved. All right, so let's talk about our particular solution. We'll start, our first piece is e to the x. Do we need to add anything else for that part? Okay. Our next piece is x squared. Do we need to add anything else? X and 1. So we have 4 pieces. A e to the x, b x squared, c x, and d. So our particular solution looks like this. So how do we find the right choices for a, b, c, and d? Well, we're going to plug it in. That's what we always do, right? If we know it's our solution, plug it in. So we're going to need to have the first derivative. So what's the derivative of this expression? A e to the x. 2b. Or is it not to be? That is the question. Whether it is nobler. No. Like I tell people, that's the 3rd floor of Carver Hall. I'm 4th floor. Very different. Yp double prime. A e to the x plus 2b. Now, we're going to plug into our differential equation. So, in particular, we know yp double prime plus 4yp prime plus 4yp has to equal 18e to the x plus 8x squared. I'm just showing you where we're going. And now we begin. A e to the x plus 2b. That's our double prime. Plus 4 times a e to the x plus 2b times x plus c. Plus 4 times a e to the x plus bx squared plus cx plus d has to equal 18e to the x plus 8x squared. Now, what can we do? We can combine like terms. I like that. We're going to combine it based on the function. Okay, so, for example, for the e to the x's, what do we have? An a of 4a. Don't forget about the 4 in the front. Remember, parentheses are friends. We've got to respect them. And these things are going to distribute in. So we have an a, a 4a, and a 4a again. It's our 4a into the subject. Okay. Well, what's our next function? Let's do our x squareds. Do we have any x squareds? 4b. Do we have any x's? There's a 8b and a 4c. Do we have any constant terms? 2b, 4c, 4d. All of this equals 18e to the x plus 8x squared. Okay, now here's a fun fact. If two things are equal, the coefficients have to match. So for example, this coefficient of e to the x has to match that coefficient of e to the x. So what does this a plus 4a has to equal? 18. Okay, similar, this coefficient of 4b has to match the which is the coefficient of x squared, has to match the coefficient of x squared there. So what does 4b equal? 8. And similar, 8b plus 4c has to, wait, there's no x. Oh, shoot. What happens? Yeah, it's 0x. So that has to equal 0. And of course, bringing us home, this part also equals 0. So now we have our system of equations. We actually have 4 equations for unknowns, but it's not that bad. So for example, what does this first equation tell us? 9a is 18, so a equals 2. 4b equals 8, so b equals 2, not 3. 8b plus 4c equals 0. Well, we know b equals 2. 16 plus 4c equals 0. So what is c? Negative 4. 2b, that's 4. 4c, negative 16, plus 4d has to equal 0. What is d? d is 3. And now we solved our coefficients. Our coefficients are no longer undetermined. So our answer, well, we come back and throw in the coefficients. So it's going to be 2e to the x plus 2x squared minus 4x plus 3. Yes? All right. We have the idea, right? We have the particular solution. We feed it in, gather, set coefficients equal, solve. We have our idea so well. Your turn. All right. So, you check the homogeneous. There's no overlap. You set up your differential equation. There's 3 pieces. Take the derivatives, plug it in, and gather. Now here it gets interesting with sines and cosines because they get to do a little bit of intermingling. 2 equations, 2 unknowns. You can solve, and you get your solution. So, all right, well, that's it for today. Come back next time for a totally new idea. Have a good day.